I'm Ian McInerney from Imperial College London, and I will be presenting work done with my colleagues at Imperial College and University of Genoa, where we have created a framework for nonlinear predictive control using derivative-free optimization as the solver. The framework I will be presenting is going to use the mesh adaptive direct search method for performing a structured search over the optimization space. The MADS algorithm has a linear complexity growth with the size of the search space. To do this optimization, we're going to augment the dynamics of the system with a state for the integral cost and a state for the constraint violation to measure those over the time, because we then perform a single shooting simulation of that dynamics for each of the candidate input trajectories. In this presentation, I'll go through some brief preliminaries on model predictive control and the MADS algorithm. I will then introduce our NMPC framework using this algorithm, showing it with a numerical example, and concluding with a discussion and some future directions of research. The problem we're trying to solve is nonlinear model predictive control, where we're trying to optimize the future trajectory of a state, of a system, given a cost function here where we have both the terminal cost and a stage cost, the Lagrangian term. We're using continuous time problem formulation, and we have the dynamics F, where we have the states X and U and the inputs U. We have the path constraints G, and we have boundary constraints H. We're optimizing over the states, inputs, and the final time TF in this formulation. Why would we want derivative-free optimization? Most methods of solving this problem are first and second order methods, and those require derivatives of the dynamics, cost, and constraints to be available for the solver. Computing these derivatives can be difficult, though, if you have complex nonlinear models, black box models, or data-driven models. Sometimes this could even be impossible to figure out if you have very complicated data-driven models. Instead, derivative-free optimization only requires that we have a simulation model of the system. So if you can simulate forward in time, you can use derivative-free optimization with nothing else, no other information needed. We use the mesh adaptive direct search method, or MADS. And in MADS, what you do is you define a cost function f at the beginning of your algorithm. Then you will choose an iterate c, and you're going to create n plus 1 pole points, where n is the dimension of your search space, that are surrounding that iterate on a mesh. That mesh allows you to subdivide your search space and choose points easier. And all those points are located in a frame surrounding it. So that frame is where you're going to be searching. You can evaluate these pole points all in parallel, and then we're going to choose the one that has the lowest cost value and use that in the next iteration as our iterate, and choose n plus 1 pole points surrounding that point. If we have found no pole points with a smaller cost than our current iterate, we will shrink the mesh and the frame to try and search more locally around the current iterate. This means that at the end of the MADS algorithm, we will eventually end up with a very, very small frame surrounding our iterate, plus an almost infinitely dense mesh. So we will essentially be able to poll anywhere around the current iterate. When implementing constraints in MADS, one way you can do this is with using a formulation called the progressive barrier constraints. What this means is you relax the constraints and measure their violation for each pole point. You will then keep both a feasible and an infeasible iterate at each iteration. And you will poll around both of those iterates. When you find an iterate that has lower cost and is feasible, you can use that to initialize the next feasible iterate for your next iteration. And if you find a point that has a lower constraint violation but might not necessarily be feasible, you can reinitialize your infeasible iterate as appropriate. More information about this can be found in the Audette and Dennis paper listed on the slide. In our framework, we use a search space that has the input trajectories u and the final time tf. We will augment the system dynamics with new states that represent the Lagrangian term of the cost and the violation measure for the path constraints. We then use a single shooting simulation of the augmented dynamics at each pole point to figure out the cost value of that input trajectory. We then implement the path constraints as progressive barrier constraints in the MADS framework, using the final measurement of the constraint violation as the progressive barrier term. What this means is for augmenting the dynamics with the cost, we introduce a new state L, which has the dynamics which are simply the Lagrangian term. So we're just integrating the Lagrange cost for each dynamic step. For the path constraints, it's a bit more complicated, but we're basically turning the path constraints into an L1 penalty. So we're going to look at the violation that we experience over the entire horizon, integrating that, in forming the state V. That means our dynamics are formed by V dot is G plus, where plus is going to be this max of 0 and G. The overall black box function we use in this MADS framework is as follows. We take in a pole point C from the search space algorithm. We will reconstruct the input trajectory U that we're going to use. This reconstruction can be either treating C as if it were just a piecewise constant input. It could be treating C as if they are coefficients to an interpolating polynomial, or any other way of representing your input trajectory and rebuilding it in the function. Then in step 2, we will simulate these augmented dynamics using an appropriate solver. In this case, we show them as possibly DAE or ODE, so you can use whichever solver is appropriate for your problem to just simulate these dynamics forward in time. After the simulation is complete, we compute the violation of the boundary conditions at the start and end points, and we introduce this row term to allow you to also weight constraints amongst each other to possibly have some that are more appropriate or more heavily weighted in this progressive barrier term than others. The overall constraint violation is then these boundary condition violations plus the final state of this V term. And V is the state that we introduced to track the path constraint violation over time. So we'll be taking the final time of that state. That then forms H, which is what is passed into MADS for computing the progressive barrier term. The cost function is going to be the terminal cost plus the value of the state L, which represents the Lagrangian term, at TF. So this is going to give us the value of that integral in our cost that we then add on to the terminal cost. To demonstrate this, we've run a numerical example where we're wanting to make a rocket reach an apogee of around 10,000 feet. In this case, though, the drag coefficient and specific impulse are uncertain, but we know that they are within certain bounded ranges. It turns out that by monotonicity properties, we can simulate trajectories with both lower bounds for the drag coefficient and specific impulse, and both upper bounds for those two, and we will have a upper and lower bound for the trajectory of our system. In this case, we're going to be using a piecewise constant input trajectory representing the thrust, and we're going to be allowing the switching times to vary. We've introduced a path constraint to limit the velocity to less than 150 meters per second. This is representing a modeling constraint where we only know these bounded ranges of uncertainty when the rocket is traveling less than 150 meters per second. The cost function we're going to use to make it reach this apogee is we're going to examine the difference between the upper trajectory, so this is with the upper bound on the drag coefficient specific impulse, and the lower trajectory, which is going to have the lower bounds on the drag coefficient and specific impulse. We're going to look at the maximum difference between each of these and the target altitude, and we're going to try and minimize that maximum difference. So running this, we can see here the altitude profile that we find. We have the upper trajectory in red and the lower trajectory in blue, which are mostly near the 3,048 meter altitude we're hoping for. We can see the velocity profile that it has found, where we're increasing. We hit that constraint of 150 meters per second and then decreasing. And we can see this thrust trajectory, where we're running at full thrust, then we're switching in between, and then we're running at zero thrust. So we can have this bang control with a singular arc in the middle. Then we can see here a little bit about the constraint violation. So this is looking at what the constraint violation is doing over time in this simulation. This is non-zero in this case, though, because of, unfortunately, how we had to implement this in the MAD solver we have access to. Unfortunately, we weren't able to use a full version of the progressive barrier constraint, and instead we had to resort to turning those into a penalty on the cost. So we have a little bit of a non-zero violation, but when this becomes an actual progressive barrier constraint, we'll be able to have those separate feasible and infeasible iterates to get violation of zero. So the augmented dynamics formulation is actually an easy way to include these constraints in the formulation, because there's no need for any separate mesh refinement step for the constraints or integrating the costs after you've run the simulation. The downside is it can possibly degrade the performance of your ODE or DAE solver, because now you've coupled in the complexity of the constraint formulation into that solver dynamic, into the dynamic solver. So if your constraints can end up creating a stiff system, you will need to then use a solver for a stiff system when you might not have had to in the past. So overall, I have presented a preliminary framework that uses this mesh adaptive direct search as a derivative-free solver, and we've defined a new method of doing augmented dynamics to measure the constraint violations that feeds into this framework. Now, this is its initial work, and some future directions that we can look at is to investigate other input trajectory representations. So the example I gave here was only a piecewise constant input, but you can also use, for instance, the search space over the coefficients of interpolating polynomials or other types of search spaces. We would like to see if we can integrate multiple shooting into the formulation, because right now we are doing a single shooting simulation, which means we are possibly going to have problems with unstable dynamics or other types of issues that we normally see with single shooting. We also want to see about improving the warm starting performance of MADs so that this can be used in closed loop applications. We've presented here an initial open loop simulation. However, we think that MADs can be used very well in a closed loop simulation with some tweaking. We also would like to investigate the parallelizations that you can find inside the black box function, so those can complement the parallelizations that you can get from evaluating all the pole points in parallel as well. So we believe there's kind of a nested parallelization that we can take advantage of as well with this formulation. Thank you for your time.